Hi, my name is Sophie, and this is my Lab 1 presentation on constant velocity motion and computational modeling. The purpose of this lab was to observe the motion of an object moving at a constant speed without changing direction, and to compare an observed model from tracker to computational model created in GlowScript to determine which more accurately predicts position. As a preview of the results, the observed final position was 0.755 meters, while the computational model predicted 0.582 meters. Although they differed about 0.717 meters, both models showed nearly constant velocity motion. The main physics principles used in this lab were Newton's first and second laws. Newton's first law states that an object in motion will remain in motion unless otherwise acted upon it. Newton's second law, also called the momentum principle, states that force net equals the change in position over the change in time. This means that the net external force acting on the system equals the rate of change of its momentum. Since the marker moved at approximately constant velocity, this implies the net force in the horizontal direction was approximately 0. We also used the relationship position equals initial position plus velocity times time, which was allowed because we are assuming that velocity is constant. Some assumptions that we made were that friction is negligible. Although friction exists, we assumed it was small enough that it did not significantly change the marker's velocity. And the second, acceleration was assumed to be 0. Since acceleration is the rate of change of velocity and the velocity remained approximately constant, we modeled the motion with 0 acceleration. These assumptions justify using a constant velocity model. Next, we have the experiment, the system was defined as the expo marker, and the surroundings include the table, meter stick, air, and earth. The materials used were an X marker, a meter stick, a flat table, and a camera. The meter stick was placed in view to scale the video correctly. The camera was kept steady to avoid measurement error. The marker was given a single push and then allowed to move freely without continued contact. And then after that experiment happened, we moved on to tracker, which tracked the position of the marker, going frame by frame and generating a position versus time graph. Since the motion occurred horizontally, we didn't need to consider the Y position. Then after that, we moved into GlowScript. In GlowScript, I first entered the initial position of the marker at time t equals 0, which was taken directly from tracker. I also defined the time step delta t equals 0.01, initial time t equals 0, and initial velocity was given from the calculated tracker data. Then that's wrong side. Anyways, next I wrote a loop that ran while time was less than the final recorded time. Inside the loop, position was updated using x equals x plus v times delta t. Because acceleration was assumed to be 0, the velocity remained constant throughout the simulation. After running the code, the program generated predicted position values over time. This produced a computational model that we can compare directly to the tracker data. And finally, we can compare results. When comparing results, the observed final position was p final equals 0.755 meters, and the computational final model was p final equals 0.582 meters. This means the observed marker traveled further than predicted, with a difference of 0.17 meters. This suggests that the marker's velocity was not perfectly constant in reality. The computational model assumes strictly constant velocity, whereas the tracker takes into, it doesn't calculate the friction, but it is affected by the friction. Possible sources of error: the marker's velocity not being perfectly constant, minor direction changes due to an uneven surface, friction not being completely negligible, small measurement inaccuracies in tracker. These factors would cause deviations between the observed and computational results. What if we flip the direction of the coordinate system? The magnitude of the distance traveled would remain the same since the distance is independent of direction. However, the signs of position and velocity would change. The physics would not change, only the coordinate representation. This means, what does this mean? It means the experiment demonstrates that when net force is approximately 0, an object moves with constant velocity consistent with Newton's first law. It also shows that the computational model depends heavily on assumptions. When we assume perfectly constant velocity, we simplify the system, but small real-world forces can still create measurable differences. Overall, both models showed similar trends, validating our understanding of constant velocity and motion. Thank you for watching.